And again, you know, normally I would do an entire semester. I would teach rock mechanics, rock engineering, and so to try to synthesize it into a course in terms of what's important when it comes to slope stability analyses, I'll really maybe diverge a lot away from sort of theory of what happens in the laboratory and really talk about it from two different angles. One being this question of, are we approaching the problem from that of a continuum or a discontinuum? And we know that in our different modes or mechanisms of failure, we have those that are controlled by bedding planes or by jointing, so planar failures or wedge failures. And we'll see that there's a series of exercises and calculations we can do for these type of failures. These are our structurally controlled failures. And if we're talking about structurally controlled failures, Aldridge had mentioned, there's very little internal deformation in these translational failures of the mass itself. So the strength that we're interested in the analysis is the strength of the shear plane that the sliding is occurring along. So in this case, we're looking at the discontinuity shear strength. And that's one thing that we focus on, and is what is the strength and how do we think about it theoretically, how do we test for it in terms of coming with strengths of the discontinuities. In other cases, in weak rock, or maybe deep-seated rock mass failures, we get more rotational type or compound type failures. And in these cases, there is internal shearing of the rock mass. And so now it's not so much, or it's not only the strength of the basal shear surface, but it's also the strength of the rock mass.
One comment, please. This is the La Conchita failure, and the movie that you saw this morning was taken just here below the center of the photograph, to the right slightly. Yeah. That's where the cameraman was standing when he took that flow slash failure. This is before that. This is how it looked 5 years ago.
So in these cases, we're moving towards then trying to understand the rock mass shear strength of the mass that's involved in the failure. So these are our two different branches that we move towards. And we have analyses techniques that focus on failures that are translational or controlled by structure. And we have analyses techniques that look at rock mass failure. And if we're applying an analysis technique that looks at translational failures or structurally controlled failures, we're interested in the strength of structures in the rock mass. Otherwise, we're interested in what we would refer to as an equivalent continuum, the combined strength of small-scale discontinuities and the intact rock within the rock mass, as these failures generally are passing through a combination of joints and intact rock bridges. So it's a combined effect that we're interested in. So first we'll look at discontinuity shear strength in terms of talking about rock mass properties. I already mentioned the data collection stage where we go out and we do mapping. There's a number of geometrical properties that we're looking at. So we're not only interested in the strength of the problem, but how these joints and the structures are spatially oriented. I mentioned our scan line mapping. So this is where we take a line across our rock mass, and we use that as a systematic control. Now, the reason for the systematic control is that we might come to this outcrop, and we want to map it, and we might just fixate on large discontinuities, those that catch our eye. And so we almost have a form of bias that comes into the mapping, a form of bias that is sort of a human bias. So the scan line provides a systematic means where you're sort of training yourself or focusing or forcing yourself to map all the discontinuities that cross that. Now there's a bias that comes in the mapping because this is a line, and there's a three-dimensional nature to the outlet, to the outcrop. But this is something that can also be corrected for. So you're trying to come up with a systematic means of forcing yourself to map. And these line lengths are normally between 50 and 100 meters, where again you set up your line and you map everything in a systematic means. And what we're trying to get a picture or feeling for are things that are related to the orientation of the surface, so the dip and dip direction of this discontinuity, the spacing, how close are these are discontinuities from the same joint family or joint set. How persistent are they? Are these features that are on the scale of tens of meters, in which case failure might occur solely along one of these features, or are they smaller? Are they limited in their persistence to maybe 1 or 2 meters, so that you have a combined strength where for failure to occur, some intact rock fracture has to occur. And any intact rock fracture that occurs in a rock slope failure brings a lot of strength to the picture in terms of cohesion. And I'll talk about that in a bit when we get further into the lecture. So there's a number of things we're looking at, and roughness is the other key parameter. How rough is that surface? Roughness basically plays into frictional strength. Persistence, in a sense, plays into, to a certain degree, the cohesive strength of the rock mass. And I already showed this. We'll have some mapping sheet where we go through these through our scan line. We'll collect our data, and when we come back to the office, then we have to try to start translating what we've mapped into strength properties. The orientation information, the key, what we're looking for is dip angle and dip direction. If you're used to doing outcrop mapping from a geological perspective, you'd be mapping strike and dip. We turn that around 90 degrees, and dip direction is the useful parameter that we use. It's what we use in our stereo nets. And I'll talk more about this tomorrow morning when we talk about how to use stereo nets to get a first indication and feeling for what type of failures might develop. But just to summarize, we do map a large number of surfaces, a few hundred of these. We start seeing some clusters. We can then start contouring them to look for concentrations. And from these concentrations, we'd pick out what are key discontinuity sets. So we're sort of averaging a sort of a scatter of discontinuities here, and we come to some center location where we say, okay, this is our, a key discontinuity set. This is another key discontinuity set. Here's maybe another key discontinuity set. The important thing, again, is to remember that this is a tool, and we don't want to be blinded by our tool. We'll use this to find the key discontinuity sets that will tell us what possible stability mechanisms may develop. At the same time, we might map a few hundred joints here to get this sort of statistical feel or representation, but it only takes one persistent discontinuity, maybe a fault plane, to control a failure. And a single discontinuity, for example, a fault plane, will only appear as a single point amongst all these scatters. In fact, it might appear as a single point where the scatters don't appear. So the stereo net and the stereo net analysis is the key tool, one of the key tools we use to do a rock slope analysis, but we can't, again, adhere to just a single tool because we might miss some feature that is actually the source of the problem, not our joint representation here. When it comes to surface roughness, there are actually two parameters that we're looking at over the persistence of the discontinuity that gives us some feel for the frictional strength that's available on that discontinuity. And we sort of refer to it as a first order and a second order roughness. Now, on a very small scale, we can measure just the roughness of the surface. We can feel it with our hands. We can see if it's polished, if it's slick and sided, or if it's rough, there's angular asperities that are involved. So we might see that there's a sort of a certain roughness that the overall surface has. At the same time, our surface might have a general roughness, but it also changes its orientation in terms of having a waviness to it. And so this waviness is a sort of a first order roughness. Our finer scale one we refer to as a second order roughness, and both of them play into the overall strength, and we have to sort of, when we think of the contribution of roughness and the contribution of waviness to the strength, it sort of comes into play in terms of the scale of what we're looking at, especially when it comes to wedge failures or planar failures. And it also approaches how we start thinking about mitigation, and we'll talk a little bit more about mitigation in terms of rock bolting and anchoring. But we use the roughness and the waviness of the surface to basically use the logic that for one surface to slide over this surface, it has to be free. There has to be enough forces involved. It has to be free to be able to ride up and over these waves, or on a smaller scale, shearing through the different asperities here. And this really comes into play when we start putting in anchors and we start bolting and tightening the rock together. We can basically use this principle of roughness that I'll explain in a little bit more detail to allow the rock mass to contribute a lot on its own to its own strength in stabilizing. So the surface roughness is the key parameter that we're really trying to get out of the rock mass in terms of what we need for input, or at least defining a range of input for strength properties when it comes to our analysis. For most questions of rock slope design, roughness is basically equated to a friction angle. We assume zero cohesion. There might be cohesion, but cohesion adds a benefit. And so we're usually trying to, if we're going to err, if we're going to make a mistake, or if we're going to say, okay, we have a lot of uncertainty, if we're going to go one way or the other, we try to be conservative. So any cohesion that is there is going to bring a benefit to us in terms of more stability than we're expecting. And it's better than to assume there's cohesion there and that you have this strength and then find out afterwards that it wasn't present. So we generally assume zero cohesion unless we have some clear indications that we can rely on a lot of cohesion. And this clear evidence would mostly be that the persistence of the joints that we mapped are quite limited, which means there's quite a few rock bridges that might come into play when we have a sense of cohesion. So the shear strength of a fractured rock mass is related to the degree of jointing relative to the intact rock itself and the strength the intact rock has. Now, Aldridge mentioned the uniaxial compression test, and that's the general sort of index test that we use for rock strength. But again, when we get into a rock mass, the intact component of the rock mass generally does not come into play. So what we're generally looking at is assuming that we have clean joints or clean discontinuities and they have zero cohesion. So we start with the assumption of zero cohesion, and then our strength really is a function of how rough that surface is. Very rough surfaces have more frictional strength, smooth surfaces less frictional strength. And if we have maybe some kind of infilling, for example a clay, that all of a sudden creates then something that might even have a lower frictional strength than we need, maybe some cohesion, but again we're looking then basically at this range of strength. The rougher the surface, the more friction that we have. And this is a very tricky thing. We're not coming out with a single number. We're basically doing mapping where we go into the field and we're basically giving a roughness of 1 to 5. You know, where in our minds it's very subjective. Each person, if I sent a different person up mapping, they'll come up with a different scatter of roughness values. But we're not trying to come up with a single value. We just want to know a range. Are we looking at approximate roughness angles of 15 to 25 degrees? Or is it 25 to 40 degrees? We want to know what kind of range we're looking at. So again, we might have the presence of gouge or weak clay that gives us some cohesion, but again, we try to be conservative in the assumptions that we make. How do we get these properties? Well, if we have some money available, we might collect samples. We might do some shear boxing tests. Important projects, for example, again, something like a hydroelectric project where the abutment is basically a very sensitive issue in terms of stability. We might do some in situ tests to try to get a feeling for the frictional strength of these joint surfaces. The shear box test, again, Aldridge, probably won't go into much detail because Aldridge has sort of explained this in terms of soil. In rock, what we're looking at is instead of shearing through more intact clay sample, we're trying to find two mated samples of rock that represent that discontinuity surface. And we'll do a shear test on there where we'll get some peak strength and some feeling for the residual strength. And so in terms of thinking about slope movements, maybe if we were dealing with something where there's very little indication of movement, so small displacements, we're looking at a behavior of something that might start behaving somewhat elastically and will have a higher strength as opposed to something that has a long history of movement, for example, a relic shear surface, where we're moving more into the post-peak area and where we're then working with using residual strength. So there might be a question of whether we're using peak strength or residual strength with a rock slope analysis, and it generally comes in terms of any indications of movement, or again, how much you want to err on the side of caution. Now the test itself is difficult in terms of actually doing laboratory testing, because it's not a unique test where you do one test and you have all the information you need. Frictional strength is dependent on the amount of normal force you apply. So if I just, without leaning on my hand, I can easily move it across that table. The more weight I put on it, the harder it is to move. Normal force, normal stress increases our strength. And we can see here where if we increase the normal force placed on a sample, our shear strength here increases. And this is how we would carry out a test. We would do a test at one confining pressure or with one normal component, and that gives us 1 point on our chart. And then we'll do 3 or 4 different normal stresses, and from that we'll draw a straight line through the data, a relatively straight line if everything lines up nicely. And from that we have our strength envelope that describes the strength for different stress states. So we're saying that with increasing normal stress, we have increasing strength, and that strength is the frictional component of strength. As Aldridge mentioned, the cohesion is not dependent on the normal load. This is again, is just to reinforce, this is a key principle, because this is basically what we're doing when we're doing rock bolting or anchoring. We, at least in terms of active support, we come and we tension a bolt across a surface. We're adding a normal component of load to that rock mass to allow the natural frictional strength of that rock mass to work for us in giving us more strength. And again, where the line intercepts our axes, our shear strength axes, we have our cohesive strength. For a lot of joint surfaces, though, we have zero cohesion. In trying to understand the mechanics of the problem and why roughness is working for us and how we can use roughness, we have to also understand the same principles that Aldridge mentioned for soil in terms of contraction and dilation. So if we think that we have a rough surface here, depending on how much of a normal load that we apply here, if we have zero normal load here, and this surface here is free to move over the other surface, then the strength is really just the strength of the roughness on a very fine scale on the surface. So it's not the second order roughness, but really only the first order roughness, because this block, upper block, is free to move up and over the second block. As soon as we increase that normal load and we make it difficult for this block to ride up and over, the other option then is to shear through those asperities. And to shear through the asperities, that's providing added strength in terms of having to shear through sort of an intact rock component. So a rough surface that is initially undisturbed and interlocked will have a peak friction angle that is made up of not only the frictional strength of the surface, but a roughness angle representing these asperities. But if we have increased normal stresses, and so dilatancy is basically reduced, or the freedom to dilate is reduced, then we have asperity strength coming into play, and with shearing, these asperities become damaged. So initially we might have a lot of strength, but over time then our strength is moving towards a residual strength as these asperities are ground down and you know, maybe even forming a bit of a gouge material. But as they're ground down, we're moving then towards our minimum value, which is our residual strength. And so we have to sort of make observations to see, if we're looking at a natural slope, how developed the failure is in terms of whether we're really counting on peak strength or residual strength. So it might not show up here with the lighting, but this would be from a shear box what the sample looks like before shearing. After shearing, we can see that the sample isn't evenly disturbed. It's only areas where the asperities were greater than in other areas where they've now been sheared off. That's what was providing the strength, a peak strength leading down to a residual strength. So again, we're looking at these areas here, these rough areas that are sheared off. So taking that from a lab environment and thinking about that in terms of a rock slope, and this is a key difference too for people who are doing rock mechanics and maybe work underground in tunneling projects and as well as slope projects. In terms of rock slopes, we're basically talking about an unconstrained block in most cases. So a block that is free to dilate and move because the only normal force that's being applied is the weight of the material itself. But it's got a free surface on the top, so if it wants, it's got a wavy surface here. It's free to move down that it's more free to move down that wavy surface than, let's say, an underground environment where there might be other blocks that are pinning it in. So if a rock block is free to dilate, then the surface roughness and the waviness will have a diminished effect on the shear strength. And again, as I mentioned, this is what we're trying to achieve when we're talking about rock anchoring. We're not relying on the strength of the steel itself to hold that block in. We're not saying, oh, we're adding these anchors here and it's the strength of the steel that is providing the resistance. Yes, the strength of the steel does provide some resistance, but what we want to do is we want to take these little nuts here, we want to cement in the end of our anchor, and we want to start tightening it up. And by tightening it up, we're adding a normal force across these surfaces, and we're allowing the roughness and the waviness of that surface to provide our strength through the interlocking of the two surfaces. So this is one thing that we're trying to use the waviness and roughness as much as possible, but we also have to look at especially on a large scale, when we're talking about, especially when we're talking about faults, we're usually then talking about something that has accommodated a lot of shear, and we're moving then from a peak strength envelope to a residual strength envelope. And it's a residual strength envelope that where a lot of these disparities have already been sheared, and we're talking about then a minimal, our minimal strength condition that we then have to consider or work towards in our design. So fault zones are also treated generally as having zero tensile strength, but they may have, and they do have lower frictional strength than tensile jointing in most cases. There might be some cohesion due to gouge, and a lot of this will all depend on their tectonic evolution. So this is some work that one of our doctorate students here, Susanna Lofts at the ETH, she had done. And just going from intact rock to the gouge zone, it's just not a matter of two materials. You might be passing through a range of materials. There's a lot of work being done by a colleague of ours in Vancouver, Doug Stead, who's looking at this in the context of rock slope failure, how these different zones also contribute to the development of a failure. And we see that on the one case, undisturbed rock has very high strength, very brittle, whereas we move into more and more damaged material. We're moving to a central gouge material that is very plastic, very low strength in terms of its characteristics. So we might need to account for a range of materials around these fault zones, especially given that fault zones are long, extensive features that might make up a large percentage of a shear plane. And so just to finish up talking about discontinuity strength, we get into these little handy tables. This is from Duncan Wiley's work, and Duncan Wiley is a consultant who does a lot of rock slope stability work. And his rule of thumb is when he's trying to estimate strengths is that he takes this table of back-calculated strengths from previous failures, and he basically says that if he has a strength property from some kind of geological assessment or laboratory test that plots drastically differently than all these points here, so as an outlier point, he doesn't trust that lab value. He's more comfortable when the properties that he uses in his analyses falls within zones or ranges of properties for which he has some previous experience or a previous history of working with. So again, it's just saying, looking at the values that you have and how they correlate or correspond to previous experiences. Now, when the failure isn't discontinuity controlled, we're moving then towards rock mass strength. And rock mass strength, we talk about it as a continuum. And when most people talk about a continuum, they think of intact rock. for a large part, when we're talking about rock mass failure, we're basically saying joints are important, but they're not important in terms of controlling the failure. They're only important in terms of contributing or being a part of the overall rock mass strength. So when I start talking about continuum, and sometimes we talk about it as intact material, it's not really talking about it as an intact material. It's just saying as a rock mass, the joints are only affecting the strength. They're not controlling the failure in the same manner as a structurally controlled failure. When it comes to rock mass strength, we can use criteria developed in the laboratory, and in the laboratory we are testing intact rock. Aldrich mentioned Mohr Coulomb and how it's a linear envelope, and when we talk about rock masses, we try to move away from a linear envelope into one that's sort of more nonlinear. The nonlinear envelope that is quite commonly used in rock mass analyses is the Hoek-Brown criterion. Both are empirical. Mohr Coulomb has maybe more of a, we have more of a feeling of it in terms of physical properties. We can think about cohesion as glue, maybe intact rock in between joints. We can think of it as a form of a cohesion, a glue. And friction we can think of in terms of roughness. So we can actually think about these in terms of physical behavior within the rock mass. The Hoek-Brown is a little bit difficult. Essentially what the Hoek-Brown is Everett Hoek, who developed the system, basically took a large number of laboratory tests. So he took 20 tests of granite, fitted a curve to all those data, took 20 tests from limestone, fitted curves to all those data, and just basically started picking out parameters from fitting the curves. Basically this M parameter and A parameter were curve fitting parameters that just, where he was able to develop a table for different values for rock. So there's nothing that we can really feel grounded in terms of the strength. In both cases, we want to work in different stress space, so sigma 1, sigma 3 stress space. For those not familiar with those terms, we're just talking about the major principal stress and the minor principal stress. It's just another way of talking about stress, the same way as we're talking about shear and normal stress. We can talk about it in terms of the principal stress components. Again, the Mohr Coulomb, very commonly used in terms of soils, very applicable when it comes to joint strength, when we're talking about the shear strength of a joint surface. But it does break down when we start talking about rock mass and intact rock strength. It's still a good approximation, and given, I guess, all the uncertainty involved, there really is no real need to mistrust it. But it's really the Hoek-Brown that we move towards. To start with Mohr Coulomb, though, just to talk about what's happening in a rock mass, we can take our slope, and we can consider just the rock behavior at different points in that slope. And we can think about it in terms of our stress space, that if we think about a rock here under deeper cover, the stresses acting on it are much higher than something maybe under lower cover. And if we think about stresses in Mohr Coulomb space, we're thinking about stresses acting on a shear plane. And so it's the shear plane of failure through the rock mass that we're interested in. So here's our failure envelope that describes the strength of our material. And so we might have a material here at depth. Even though the stresses are higher, the deviatoric stresses, the difference between our major principal stress and our minor principal stress, is such that our stress state here is in a stable condition. It doesn't, and by stable we mean that it hasn't exceeded, it doesn't touch or want to exceed this failure envelope. At another point in our slope, though, even though our stresses might be smaller, we might have a situation with the deviatoric stresses relative to the failure envelope where we might have failure. And then this is something where might be something then that would be an element or a point on our eventual shear surface. And of course, there are a number of soil or rock elements on that shear surface. But this is the idea of using Mohr Coulomb as a shear strength criterion, trying to decide where shear occurs in the rock mass. And I just want to emphasize that this is different when we're talking about structurally controlled failure and shear along a joint surface. Same language, just in terms of the nature, though, of the failure, we're talking about two different scenarios. One where we have translational failure controlled by a structure. Here we're talking about maybe something more rotational or a compound failure that's passing through the rock mass, passing through discontinuities and other planes of weakness within the rock mass. So the problem with Moore Coulomb, at least in terms of observations, is that it seems to be quite limited when we're talking about both intact and rock mass strength. And this is because when we look at these curves, we see that the envelopes aren't linear, as Moore Coulomb predicts, that they're nonlinear. And where we really get messed up is under low normal stresses and tensile conditions. And when we talk about rock mass failures, we know that we generally sometimes have low normal stress conditions, especially at the toe of the slope. And at the head of the slope, we have tensile conditions. And this is where we see tension cracks opening up. It tells us there's tension occurring. And Moore Coulomb sometimes gives us problems in terms of properly analyzing those stress states. Again, it's because we sort of have, instead of a straight line that comes out here, where we have a much higher tensile strength with a Moore Coulomb assumption, even if we sometimes use what's called a Moore Coulomb cutoff, we see that the failure envelope, especially under low conditions, is more nonlinear. And so Everett Hook moved in terms of recognizing this and finding that he had a number of problems with a lot of the projects he was working on between the linear envelope and the nonlinear envelope in terms of properly predicting the stress state, that he sees that slope failures, especially, are ones where the different types of stress conditions that you see are ones that fit more closely to this nonlinear failure envelope. So that being said, most of the work is in the last, let's say, 5 years in rock slope analysis has really moved towards better implementing Hook-Brown criteria within an overall framework for stability analysis and rock mass strength. And the way it works is saying that one of the problems we have is that we test a lot of things in the lab, and then we need to scale it from lab strength to rock mass strength. And we say this is because we're testing intact rocks, and the rock mass itself is jointed. It's weaker than what we test in the lab. So we need a means to be able to scale the intact strength that we get in the lab to a rock mass strength. And this was one of the primary focuses in the development of the Hook-Brown criterion. In a sense, the two key parameters, M and S, can then be equated. They're not exactly equal to, but they can be equated, that M is sort of equated to a frictional parameter, and S, in a sense, is equated to a rock mass coefficient. That you have an S value of 1 for intact rock, and then the more fractured the rock, so looking at the rock mass in general, the more fractured the rock, the lower the S value. So this is what the criterion is for intact rock, where we have a lab-determined value for intact rock, and our S value is 1. Different values for limestone, different curves fit for granite. The curve fitting parameters is M. So he did Everett took a large number of rock types where he now has a range of different M values for intact rock for different rock types, which then need to be scaled, and I'll talk about this in a second, need to be scaled to the rock mass itself. So we have MI and S values are the intact values moving towards what we want for the rock slope analysis is a rock mass strength. So adjusted rock mass and then an S value that varies as a function of how fractured and jointed the rock mass is. Now the simple way to do this, when you say, okay, we're talking about a complex system, how exact can we actually get to know the rock mass? Are we basically putting too much effort into coming up with some exact value for something where we have so much other forms of uncertainty involved that we can move aside? So I'm just curious, how many people have worked with rock mass classification in terms of RMR, the Bienielski RMR system or the Barton Q system? Maybe 1 or 2 people. These are basically rock mass classification systems that you move through and you do a very detailed analysis in a sense of the orientation of the joints, the roughness of the joints, infilling, any presence of water, in the case of Barton's Q system, the type of stresses that are involved. And Everett Hook basically said, well, this is too complex really, that really all you need is a rule of thumb. And the rule of thumb they developed is called the geological strength index. It basically moves from saying and doing a visual observation of a rock mass and saying you've got intact massive rock, or you've got jointed blocky rock, or the jointing is so dense that you're getting into either a disturbed blocky material to something that's basically disintegrated. And in terms of the surface characteristics of the joints, you either have something where you have basically good strength conditions in terms of unweathered surfaces and very rough, to something that's slick and slided, highly weathered, lower frictional strength. And combining what you see in terms of the structure and the quality of the joint surfaces, you can basically pick out a number between 0 and 100. So the GSI is basically related to the degree of fracturing and the condition of the fractured surfaces. And it's a visual inspection, very approximate. And depending on where you are, you might be working with materials that are mostly jointed. So you're usually, because of the tensile nature of jointing, you have good surface roughness. Or in terms of fault zones where you have a lot of disturbance, a lot of shearing, and you're looking more at your residual strength, you're talking about lower GSI values. And they've elaborated on the GSI for heterogeneous conditions where you're looking at interlayered sandstones and siltstones. There's a number of adaptations that this GSI system has gone through. But again, you don't want it, to me, in a system that isn't meant to be exact, you want to keep it simple and flexible and easy to use. For those who are familiar with the rock mass classification systems, the GSI is basically an equivalent of the RMR taking away the groundwater. And this is going to be a key thing that I'd like to emphasize, especially when we start talking about analysis. The difference between rock mass classification and rock mass characterization. Rock mass classification systems evolved as an all-in-one design tool that you go out, you do a rock mass rating, and from that rock mass rating, you get design specifications. And because of that, they said, well, groundwater is important, stresses are important, so they work all those things into their classification system. The tools we have now to do analyses, though, they handle groundwater and they handle stresses much better than just a rule of thumb approximation. So all we need now for our analyses is essentially the characteristic of the rock mass itself. The stresses and the groundwater will be taken care of separately. So we take the rock mass classification system of Bieniawski and we drop out groundwater. So we basically give it a groundwater rating, the highest rating, which basically says there is no groundwater. And we use that, and that's basically more or less what the GSI system is, -5. Empirical systems, you always have plus this, minus that. It's just rule of thumbs. So the geological strength index is really Bieniawski's RMR system, assuming dry conditions, and -5. And this works when you have a fairly good rock mass. If your RMR is less than 23 on a scale of 100, so getting into poor rock, then actually the GSI recommends switching over to the Q system, which is another competing rock mass classification system. The RMR and the Q are the two. They feel the Q system handles poor rock mass quality better, but what they use is called Q prime, where, again, people are familiar with Q. There's 3 quotients here. One related to the rock mass, how dense the joint system is. Another one in terms of how rough and the quality and how much frictional strength there are on those joint surfaces. And a third one that relates groundwater pressures, pore water pressures, and stresses. They drop that term off, again, saying that that has nothing to do with the rock mass itself. It's a condition that's imposed on the rock mass. So they drop that altogether and they call it Q prime. So again, these are the 2 key systems used especially in tunneling and rock mechanics analyses. The GSI is basically trying to simplify it and say, okay, instead of using these as all-in-one design tools, let's just use them to come up with a rock mass number that we then put into our design tools, whether it's a numerical calculation or analytical calculation, and use that then, and then account for groundwater and stresses separately. And this is really then the difference between rock mass classification and rock mass characterization. Rock mass classification, either the Q or RMR system, is basically coming up with a number That's an all-in-one design tool, because from this number, you get your support requirements for a tunnel opening or for a rock slope. Whereas the rock mass behavior is saying, come up with properties for the rock mass itself, and then take those properties and use it in a different tool, for example, a numerical method, which is better equipped with for handling those type of overprints in terms of stresses and pore pressures. So there's a range of behavior then that we're looking at from these characterization charts. Rock that we refer to as intact rock, although you can see it's jointed, but relative to the really fractured rock we can get into, we sort of refer to it as massive rock. Maybe massive rock is better than intact rock. And we're getting different ground responses. In massive rock, maybe we're dealing with more structurally controlled failure, wedge failures, planar failures. In the more heavily fractured rock, we're dealing with something then that is maybe a more compound type slide or rotational slide. And if we get into maybe something that's foliated rock, which is a special class on the end of this, where you have a very dense preferred plane of movement with very weak material, you get these combined failures of buckling failures, plowing failures. These are really special conditions, and I won't touch too much on these when we talk about the analysis stages. We're really looking at structurally controlled failures and rock mass failures. So just to wrap up sort of the rock mass failure, the simple way of basically going about and doing this is the failure criterion that the analyses use. You won't see that. It's hidden inside the computer. Someone programmed it. Unless you're using your own spreadsheets, and we'll do a few spreadsheet exercises, but not using Hook-Brown. We'll do spreadsheet exercises using more Coulomb, because it's easier to think about in terms of the mechanics. But this is all what's underneath the computer programming. And again, you don't want this to be a black box system where you're just happy with the pretty pictures that the computer puts up on your screen. You want to have some understanding of what's underneath it. And to get these parameters, because the computer will ask you for an M parameter, an S parameter, the A exponential factor, and the uniaxial compressive strength, you want to have then some semblance of how to go from your mapping data to getting that. The easy way is using the empirical relationships that have been developed by Everett Hook, which is basically taking your geological strength index, which is your rule of thumb, looking at that rock mass, how jointed it is, what kind of condition those surfaces are. You might say, oh, it's a GSI of 30, or it might be a 40. You don't want to fixate on a number saying, oh, it's a 33, and say, yeah, it's 33. You want a range of values. It's 30 to 40, or it's 50 to 60. That number just gets plugged in into this equation here with this MI value. The MI value is the intact value. So basically, you're taking a property that represents intact rock, and he has all these tables here from the laboratory tests of different rocks, granites, well, let's say crystalline igneous rocks, metamorphic rocks, sedimentary rocks. They all come up with their own M values and standard deviations as to the range of values that they saw in the laboratory. And that intact property is scaled to the rock mass property based on your rock mass number that you gave, your geological strength index. So the MB value, which is what you input into your analyses, is a scaled rock mass value and not the intact strength property. And that's a key consideration when we're thinking about it, because you're drawing a slope in your analyses and you're not actually putting joints into the analyses explicitly. They're implicitly in there through the scaling of the rock mass strength. And then your S parameter depends on your GSI. If your rock mass is so heavily fractured that there's really no sense of rock mass cohesion, then this S value is 0. The A exponential function then becomes, instead of being a value of 0.5 or basically an inverse relationship, you have something that's scaled to your GSI. However, if you have relatively competent rock, then your S value is again scaled from 1 being intact to some value that is reflective to that rock mass characterization you gave. Is it blocky rock? Is it heavily fractured rock? So S is essentially a form of rock mass cohesion. not intact rock cohesion, but rock mass cohesion. How jointed is the rock mass? How many intact rock bridges are in there, giving you some form of cohesive strength. For those who are working maybe in an open pit environment or with road cuts where you're doing a lot of blasting, they also work into this a disturbance factor. So saying that through blasting, or in some cases when you're looking at some certain geological processes, stress relaxation, what you observe in the field might be a disturbed state, or what you're designing for, the values might actually, the rock mass strength might actually be decreased, because if you don't do your blast properly, if you're doing bulk blasting, that adds fracturing and damage to the rock mass. So again, a very rule of thumb, just from their own experiences, nothing that you want to say that this is a theory that you can explain in terms of physics and principles, just based on their experience. So it means you just have to take it with a grain of salt. You have to factor in some variability. They can work in a disturbance factor for the rock mass M value and the rock mass S value. All this is basically coming towards, again, moving away from the idea of rock mass classification, which was basically the state of the art in the 1970s for rock mechanics, and saying, okay, since the 1970s, we've got the advent of computers. And with computers have come at least both complex analysis tools, but also simple analysis tools. And so the input for these simple analysis tools are things such as are things where we take into account what we need to get from our mapping is the rock mass strength, and then things such as the groundwater, loading, all these things, they don't need to be worked into a rock mass number. These analysis tools now can incorporate these things, so what we're just trying to do is break our rock mass into rock mass properties. M and S values, if we're working with the Hooke-Brown relationship, these can easily be converted into cohesion and friction if we want to use a more Coulomb strength relationship. A rock mass Young's modulus, a rock mass Poisson's ratio, if we're doing something that involves stress and strain calculations. And so there's also been a lot of work in terms of correlating either RMR values or GSI values also into rock mass moduli values. Again, recognizing that what we test in the lab is an intact strength or intact deformation moduli. The rock mass incorporates intact and joint, the behavior of the joints, so we need to put that all together into some kind of rock mass property. And again, there's complex equations. They're not that complex. It's just because everything is taking one curve and fitting it to a straight line that they've come up with these relationships for converting M and S values into friction and cohesion. There's actually a lot of programs that will do this for you, and there's a free one on the internet called Rock Lab that you can download from the Rock Science website. So it's a free program that helps you derive M and S values for rock mass values based on laboratory test data and so forth for your analyses. There's also a lot of information on what's called Hooke's Corner on all these values. Again, whether you're using more Coulomb or Hooke-Brown, it's just, again, to appreciate that what you get from a lab value has to be scaled to the rock mass. And there's a number of ways of doing this. The easiest one in the moment in terms of current practice is doing it through Hooke-Brown, but sometimes more Coulomb is a little bit more intuitive in terms of thinking of cohesion and friction, and there's no reason why you also can't use that, because in the end, with all the uncertainty involved, you still have to look at a range of values. You're not looking at saying, oh, more Coulomb is so superior to Hooke-Brown because when I put in my values, I get a better answer, because you're putting in a range of values. So again, user beware is the message. So I think we then move to coffee break.